Okay, so good morning, everyone. So welcome to the tutorial in KDD. So this is a tutorial in dense subgraph discovery, and my name is Aristides Gionis. And my colleague who is presenting the tutorial is Charalampos Tsourakakis. So he's sitting over there. So both of us. So I'm in Aalto University in Finland, and Babis Charalampos is in Harvard University. So both of us we have long Greek names, so that's why we have a shorter nickname that you can call us. So you can call me Aris, and you can call him Babis. Okay. So this is the material for the tutorial. So you can find it going through the tutorial website, and then you can go to our page that we give some small introduction to the area, and then you can download the slides. And also we have links to the key papers. And also in the slides you can have an extensive list of all the literature and the main references that we are using. Okay. Okay, so let me say before anything else at a very high level what this tutorial is about. So what we are going to talk today for the rest 3 hours or so. So the main setting, the main problem will be working is the following. So we are given a graph or a network, as is commonly known when we have real data sets. So graph is the more mathematical abstraction, we can call it network. And we can have different variants of this setting. So we can consider static graphs or dynamic graphs, so that graphs that grow over time, right? And this can come from the motivation of considering that data abstraction comes from real applications, that networks or graphs are used to represent social networks or biological networks, information networks, and so on, right? So this would be our input. And what we want to do is to find a subgraph, a subset of the vertices of this graph that is dense, right? So dense means that there are many edges among those vertices of the subgraph that we are looking, right? So this is like at the high level, this. So if you want to take something what the tutorial is about, is this. So what we will try to do is to answer the questions. Okay, why I care? Why I want to solve this problem, right? And in order to discuss about this problem, we will also discuss what that dense means. So dense at this point, I told you it has many edges, but I have, in order to address this problem, I have to mathematically define a measure of density and then study the corresponding problem. How do I solve such a problem? How do I find such a subgraph, right? So what we are going to do, we are going to review main problems and many algorithms for this area. So our tutorial, we have designed it so that it's quite broad. So we can have some of the classic algorithms, some elementary algorithms. Some of them go back to, I think our most key algorithms go back to 84. So it's a 30-year-old algorithm. So it's a Goldberg algorithm. We'll see it in a while. But then this is an area that over the last 30 years it has been involved quite a lot, and nowadays there is a lot of recent work on that area. So many of the papers we will review, they are of the last year, so 2014, 15, and so on, right? And so we will try to give a very broad overview, high-level definitions, what do they mean, what are the main algorithms, but also we have in the second part try to go in more detail and understand more the mathematical techniques and algorithmic techniques and tools that we need to solve these problems and so on. And we will also try to convey a lot of the applications. So to answer this question, why do I care about this problem and what are the real world applications in data mining? So this area of dense subgraph started, what I said, 30 years ago. It has started mostly in theoretical computer science, but more recently people in data mining have also found interesting applications, and they apply these techniques, but they also develop novel techniques that fit their applications. Okay, so this is the outline of the tutorial. So we'll start with some quite a few motivating applications. Again, try to answer this why I care. Then I will spend some time talking about the preliminaries. So how do I find our problem setting, and what are the measures of density? So what is the quantity that we will really try to optimize for a graph? And then we will switch to algorithms. So how do I find dense subgraphs? And then we will have two basic scenarios. So we will consider many different problem variants, but two basic scenarios. So one, we will talk about static graph. So the graph is given at the beginning, and that's it. So I want to do something, find and then subgraph and finish, right? Or a dynamic setting where the graph is updated over time. So new edges are coming, edges are deleted, and then I also don't have a lot of space to store the whole graph, but I have to do update as I go, and so on. And then we will talk a little bit about problem variants. So this will be more kind of applications that come from real-world problems. They don't fit exactly our setting, but they are kind of related, and they use the same algorithmic techniques and so on. Okay? So and then we will also try to consolidate everything and offer some suggestions for open problems. So if you want to work in this area, some problems that we think will be interesting in the future. Okay, so let me start with the application. So what would be, why do I want to find dense subgraph? So notice that I have not defined yet what does it mean dense subgraph. So talking about applications, try to have in your mind this intuitive concept that I have a graph, I want to find a subgraph that there are many edges in between. Okay, so our first motivating application is really, it's not a concrete application, it's more like of a general framework that I can apply for many different problems. So and this would be the correlation mining framework. So in that case, I have some kind of data. The data could have they come from different domains. So I could have a stock data from the stock market time series data representing the price of the stock, or they could have gene correlation network. So I could have genes, and I know I can do some string analysis to try to find out which string matches with that string, and so on. So now the concept is that I take this data and I build a graph. So where the vertices of the graph represent the entities that I have, so either the time series in the first example or the gene in the second example. And then the edges on my graph capture correlation. So of course this assumes pairwise, a quadratic way to compute these correlations, but actually for many cases there are faster ways that you can compute the correlations. You don't have to do all this quadratic computation, right? And now the answer I will try to do, the application I will try to do, is to try to find subsets of these entities that have something in common. They all correlate a lot with each other. Okay, and this can be used for analysis of stock market to find, for example, which companies behave similarly, they belong to the same group or sector of finance and so on. Or I could use to detect co-expression modules in the gene expression data and so on, right? So this is really a general framework. Okay, a little bit more concrete, so this is not a framework, but it's a concrete application that dense subgraph has been used, is in fraud detection. Here, a nice example is a recent paper, Biotel and all. So what they wanted to do is they analyze page-like data. So think of your favorite social network like Facebook. So people like some pages, and now so I can have a matrix here of so this would be users and this would be pages. So the rows are the users, the columns are the pages, and I have a value if a user likes a page. And now what happens if I manage to find a dense, in this case, bipartite graph where a lot of users, a group of users, all of them like a group of pages, maybe there is something suspicious going on. Maybe these are not real users, but bots that they have all been bought to, they have provided, let's say, the service of like to some certain pages who are the pages who have paid for this service. So maybe I want to detect that and evaluate the importance of these pages and so on, right? So this was an application. Now the question is, how do I reorder this matrix that I have no any way to order it, so in order that these kind of dense blocks emerge, right? Okay, so another application in e-commerce. So in this case, again, I'm in the setting of a bipartite graph, and I define my graph between advertisers and queries. So these are the two parts of the partition of my bipartite graph. And in this case, an edge between an advertiser and a query has a weight. And this weight is how much money the advertiser is willing to give in order to bid for a certain query, Q, the one on the other side of the B partition, right? So now this again interesting. So if I discover those graphs, these dense subgraphs in this large bipartite graph, I will be able to discover submarkets. Okay, so all of these advertisers, they are all willing to bid for those queries. So these are probably the queries that like specify the submarket, right? So it could be, for example, if they are on the wine industry, they probably bid on things like wine, glasses, I don't know, wine tasting and so on. Okay? Okay, so keep moving and now switching to a different domain, so in bioinformatics. Again, so the scenario here is very similar. So I have, I could have certain genes, and I want to, again, find associations between the genes. So I represent my genes as a graph, so the vertices, and then the edges capture this association. So, for example, I could have vertices to correspond to k-mers, and the edges represent the similarity between those k-mers, and then I want to find motifs on the DNA, right? Or I could do some gene correlation analysis, like the first example, and discover complex annotation patterns on the gene annotation data. Okay. So this is also a very interesting story, and this brings the point that I said before of dynamic networks. So you can think of all the previous examples, although this is not exactly true, but let's say we think them as static data. In this case, we think of dynamic data. And let me explain what is the scenario. So in this case, I want to identify stories. So let's say I watch a news feed or the news that are being generated from media, BBC, New York Times, and so on. And I want to say, okay, which are the stories? What people are discussing today, right? So, and this, of course, depends on what is your background, where you are, what is your feed, and so on. But we like to do this automatically from Twitter. So not just what the news media providers give to us, but what us as a users, let's say, talk about and tweet about and follow and so on. So there was a recent, 2012 paper that studied the concept of finding these stories. So the way they did it was that they take tweet, they extract some entities. So in that case, they had this kind of situation of Obama being the raid that happened by the US military and so on. So, okay, so they take the tweet and I identify this entity, and then I see if two entities, they co-occur in many tweets, then I have an edge between these two entities. And then if I have a subset of entities that all of them have many edges with each other, then probably this means that there is an underlying story about the set of those entities specified, right? So now again, this is a dense subgraph problem, so finding this subgraph among the entities and the edges will give me a story. And now the interesting part here is that this is very dynamic. So the Twitter stream is very large, so high volume, very rapidly coming. So I don't just want to, I don't have static. So this is like, I want to build an application that is standing and processing the Twitter stream and generates this real-time news stories as I go. Okay, so this is the setting. So I'm now interested on this dynamic part of the dense subgraph identification that I talked before. Okay, so this is also quite general. So in this application we are in the graph mining scenario. So our goal here, and many people have tried to address this goal with different tools and different objective optimization functions, methodologies, and so on. But our goal here is to understand a graph. So a graph is something, or a network is a ubiquitous structure. It captures a lot of data sets, but also it's very complex. So it's not easy to visualize. So how do I really understand what is going on a real graph? For example, community detection. You probably know this work is also a tool that is used to understand graphs. So this is another tool, another methodology offered very recently by Tsourakakis, I don't know how to pronounce the name, and his colleagues, and appear in the WWW conference, and they say, okay, we are not really looking at communities, let's say, a disjoint partition of the vertices, but I will try to build what they called a nucleus decomposition of the graph. So this was a hierarchy. So this will be subgraphs contained in other subgraphs. So I will build a tree where the tree is defined via containment, right? So I have small subsets of vertices, and this is contained in another larger subset of vertices, and so on. So I can build this containment so that you can see this is like of a forest, actually. And as I go up, two things happen. So first, the subgraphs become larger. So this is indicated by the size, by the shapes here. So circle is very small, and hexagon is the largest, so right, and then you get some square, so the size increases. So here it increases by multiplicative factor, but also they become sparser. So at the leaves, I have very dense subgraphs, and then as I go up, they become sparser. So this gives me this kind of a way to analyze my network and see what's happening, and then perhaps I can zoom in and see what are the different communities and so on. Right? So it's again in the composition, it's hierarchical, and the density is like a fundamental concept to make this kind of analysis. Okay, so perhaps up to this point, all of the applications are kind of intuitive and well expected. So here comes an application that one could not suspect that this has something to do with dense subgraphs. And the reason is that it doesn't come in the definition of the problem, but it comes kind of as a tool that I use in order to solve my original problem. So what is my original problem? In this case, I have a large graph, and I want to do distance queries fast. So I have the graph, and I give you two nodes, A and B, and I tell you how far is A and B, okay? So of course, we all know how to do that. We do Dijkstra. But in certain cases, this is not good enough, because Dijkstra takes, let's say, linear time or n log n time with respect to size of the graph. Sometimes I want to do it really fast. Let's say Google Maps. I want to really serve a lot of users in real time, in nanoseconds. My graph has billions or trillions of nodes. I cannot really do Dijkstra. So I want to do some pre-processing in order to store some information. And when the query points arrive, A and B, I do some very fast computation, and I'm able to tell you the distance between A and B. So there are many applications that we're going to do this type of distance queries in graphs, when, like Google Maps, these driving directions, when I want to do navigations in sensor networks, even in social networks, actually, I often do that. So I say, okay, me and Babis, okay, there is an edge between us because we are friends or co-authors or whatever, but let's say me and Jeff Webb, who is the KDD PC chair, right? So in the social network of KDD, how far we are, what is the distance between me and Jeff Webb? So we don't have a paper together, we are not related with one edge, but what is the shortest path, right? So I want to answer this type of questions. Okay, so now, of course, this is a big area. There are a lot of techniques to do that. One family of techniques relies on the idea of landmarks, let's call them, actually let's call them labels. I think it's consistent with the slides. So what happened here is that I have, in this case, this node U. Here is this square yellow node. Okay, so for that node, I keep a set of other nodes. So this would be the yellow circular node. So all of these nodes are kept as labels for this U, for this square node. So these are the landmarks with respect to that node, right? And for each node in my graph U, I keep a set of these labels. So this would be other nodes and their distance to my original node. So for example, this node is on my label and has distance 2, and this has 3, and this has 4, and so on, right? Okay, and of course you might say this is expensive, but I don't keep so many. So I have a large graph. Let's say I have n number of vertices. So I keep, I don't know, a logarithmic number of those labels. So now my space is not so bad. I can still keep and store this type of graph around. Okay, so then I do it also, as I said, for all nodes I do the same. So here is another node, V, let's say, or let's call it T. So let's call the original. Okay, and this is another node, and these are the labels of that node. Okay, and now, okay, so now the point is that if I want to compute a set of, if let's say now, for the example, that my query consists of these two nodes, S is the yellow node and T is the red node, right? And I want to compute the shortest path distance from S to T. How do I do it? Actually, let's ask this question. How do I do it fast, using this information that I just provide you, using these labels? Any idea? So since it is a small room, I think I will make some questions, but also feel free also to interrupt me so we can like keep it interactive and so on. So do you have any ideas how I do it? It's actually written, but let's say pretend that it's not there, but try to think before reading, or just try to explain me, try to spell out what is written even.
So we want to compute the distance between any of the two neighbors, right?
So
we have the distance between any two neighbors, and now we have to update.
Okay, again, so I have, what do I have? What do I ask? So I have my graph. For each node on the graph, I have the labels. Okay, what are the labels? The labels is what I said here, is some other nodes. So U is a node on the graph, and then the labels is a set of nodes V, and the distance from V to U. So for example, the labels of me are something like, okay, Bob is 1, because we are at distance 1. Mirella 1 also, because we have met before. Jeff Webb 3, or 2, because we have things like that, right? But of course I cannot keep the distances from all the graph, because this is too much, so I just keep a subset. And now I have this for every node on the graph. So then the question is, I give two people, me and the Prime Minister of Australia, and I want to find what is the shortest path. So what do I do? This is the question.
So basically find the corresponding half first. I think in your previous session you already keep every distance, paired right distance between the halves, and that will be upper bound.
Exactly, very good. Okay, so excellent. So what happens is that if me and let's say compute the distance between me and the Prime Minister. If me and the Prime Minister has one node that we have in common, I know that the distance of me to that person and the person to the Prime Minister is an upper bound of our distance. Because of the triangle inequality, our distance is at most this much. It cannot be larger. Okay? So now, among all the people that all the hubs that intersect, I take the one that is the smallest, because I want to make this an upper bound, so I want to make it as small as possible, as tight as possible. And this is the idea. So now the property that I want to ensure is coverage. So if I'm able to ensure that there is at least one person on the shortest path, then I know that I will recover the shortest path. Okay. Okay, so, but this tutorial is not about distances, it's about dense subgraphs. And the point is that the question is, how do I find these labels in order to ensure this coverage property, that for any two people there is an intersecting label on the shortest path. So this is my covering property. Okay, it turns out, so we're not going to do the why, but it turns out a smart algorithm by Edith Cohen and co-authors that a very nice algorithm, two-hop labeling algorithm, relies on dense subgraph. So that's why I said this is not an immediate kind of obvious application or motivation for dense subgraph. It's kind of, you really need to. Okay, and then we have also much more recent work So the state-of-the-art scheme and implementation of this idea with other tricks and heuristic is by Delling and al. So published last year, and there is other work on this topic. So the idea is that you use dense subgraph as a subroutine to solve another task. So that's why I said that.
Question here.
Yes.
I mean, in this kind of a context, you have to find many dense subgraphs, or perhaps all dense subgraphs in the graph. It's not just finding a dense subgraph.
Right, that's true. So I guess in many, so this is in the dense subgraph would be in the inner loop of somewhere. So maybe you, with respect to actually I don't, Bobby, do you remember exactly the construction? So
the idea is you would like to have small labels, like for every vertex you have this set of other vertices. You would like to ensure that you have this covering property, but at the same time you want them to be small. So the small aspect comes from finding dense subgraph. That's how the problem comes.
but it's like, is it like you make many calls to the dense subgraph, or you just make one on the whole graph? Okay.
Yeah, for every, on the whole graph.
Okay.
Do one computation.
There's one computation which finds all dense subgraphs.
No, you don't find all. So we discussed the concept of finding all. This actually doesn't work because you can have exponential number of them. So it's just one.
Okay. Okay. So, but this was just an application. Okay. Another kind of area that people in here in KDD might be familiar and with, and it turns out that is also relevant to the dense subgraphs, is this frequent pattern mining. So perhaps this is even how this concept of data mining started with like 20 years ago or so. Okay, so the setting, okay, I suppose you only know the setting. So I have transactions. So in transaction here is a comic, let's say comic issue, and then I have the superheroes that appear in this issue, and then I want to say which are the item sets that appear in many issues together. For example, in this data set, Iceman and Storm appears in 60% of the issues, right? So this is a frequent pair, but then I want to find frequent item set. Okay, I suppose you know this stuff. Okay, so this is one of the most well-studied problem in data mining. There are many efficient algorithms. So most of these algorithms use the monotonicity property, what you have here, like a priori and so on. So the idea is that algorithmically, that I start with a small set of a small item set, let's say only the singleton, and I know if they participate in a frequent item set, they have to be frequent themselves, and so on. And then I build up, right? And usually in this type of applications, the algorithms enumerate all frequent item sets, okay, but some other no, but okay, this is a very large area of free sets, okay. But the point I want to make is that frequent item sets and dense subgraphs are very related concepts. Why? So because this is my transaction data set, so what we saw before. Now I can represent this transaction data set by a binary matrix. So the rows are the transactions, and the columns are all the items, and I have one if the transaction contains the item. Okay, and this is exactly the same as having a bipartite graph, where the rows are the one side of the partition, the columns on the other side of the partition, and there is an edge if there is a 1 on the matrix. Okay, and now if I have a frequent item set there on this view, it means a dense biclick on this. Actually, it means not a dense, it means a biclick, right? That I have a complete bipartite graph. And then and then I have different formulation. If I have a tile, for example, or there are other formulations that they don't ask for a full support, but I might have some error. So this would correspond to dense subgraphs. So this is a nice connection. And there is also some work that they have tried to take advantage of this connection. For example, also very old work, classic work, is the work of Kumar and others in trolling. So there, what they wanted to do already in 1999, wanted to find web communities on the web, right? So now the key observation is that a community is like you take the web graph, consists of the hyperlinks, that the web community is a dense subgraph. Okay, and the observation is that if the community is dense, then it should contain a complete bipartite clique, a small bipartite clique, right? And they justify this claim. They say, okay, if the community, if there is a dense community, then the clique should be there, just by probabilistic arguments. And if the community is not dense, then probably there is no. It's unlikely that you have such a complete clique on these dense subgraphs. And then they say, okay, in order to, so let's say that this is a community. In order to find this community, I will start by applying the techniques of frequent pattern mining, find these complete bipartite cliques, and then expand them while trying to keep the graph being still dense. Okay? So this was one of the very first applications that also has some connections with dense subgraph. Okay, so I think probably there are too many applications, but let's do one more. This is some work I did with my colleagues when I was in Yahoo. So we're in Yahoo Research. So this was kind of a system type of paper that we say we wanted to optimize the throughput, the performance of a social network, let's say. And what happens mostly in the social networks are event feeds. So when I log into Facebook or Twitter, I read my feed. So what is my feed actually? So these are posts that the people who I follow have posted about. So now this internally in the system happens through transfers of data. So if a friend posts something, so this item will be written in the data store that corresponds to the space of my friend. So, and when I read something, when I read my feed, I have to take items from all of these data stores of the different people and transfer them to my data store. So I need to make this transfer. So and this transfer is the bottleneck of many of these. So the system throughput is really proportional to the data transfer between the data stores of what people write and what people read. So one question is, how do I do this transfer? So I have to transfer some data from one store to another store. So how do I do it? So in fact, there are two operations. One is pull, the other is push. So I can either, every time my friend writes something, I can push it to my store, or the other way, every time I log in the system and I want to read something, I pull from the data stores of the people I follow, and I take them. So what is more efficient? Is it better to pull or to push? Okay. For this, depends really on the consumption and production rates of the people. How do people behave with the system? For example, if someone never logins in the system, for that person it's better to pull, because once you log in, you enter once in a while, then you pull and then fine. So if you never write, for example, or very rarely write or post something, then it's better to push, right? Because then you have most of the time you don't do anything. Okay, in addition to this kind of obvious optimization, there is another optimization. In this optimization now it takes advantage of what is called the clustering coefficient in the network that social networks tend to have a lot of triangles and so on. So now imagine that I have this situation. So Z follows U and V follows both Z and U. So if I have this situation and I operate this transfer with a push U to Z, and I operate this transfer Z to V by a pull, I can forget about the transfer here. Okay? So, okay, it's not so easy to see, but you see that you can forget it, but this is the only combination of pull and push I can do and forget about this transfer, and still ensure that this guy, whenever logins in the system, reads the news all the fresh news and doesn't lose anything that somebody else has already posted, right? So now, if I want to find, okay, and now I can save one edge, right? So you might say this is not really a big saving. It's 1 out of the 3, so okay, what's the big deal? So actually, now the point is that if I'm able to find dense subgraphs in this type of data transfer setting, I can replace, so the dense subgraph will be all of these dotted edges. I can just forget about these dotted edges. I will just keep this hub. I will make all of these transfers as a push, and these transfers here from V to Y, from W to Y as a pool, and then I can ensure my property, and then I can do even quadratic number of savings on my data store. So this was, again, some application of dense subgraph that comes from the system's perspective and optimizing performance and so on. Okay, I think I will skip other applications. Just last thing I want to say is that so far I try to give motivating applications and motivate real problems in real networks. Most of them were static, except, okay, we also saw dynamic, but we also have the issue of high performance. So nowadays, we do a lot of computation not just on our laptop, but on big clusters, Hadoop, MapReduce, so to deal with really large data sets, billion of users, and so Facebook reported billion of users and 1 billion of users and 140,000 billion of friend connections, so really large graphs, and this was even 5 years ago. Now I guess it's even larger. The graph becomes denser, probably not so many. I guess we have not reached the 2 billion, I don't know, but the graphs have become much denser, so much more edges. So very large graphs, so you really want to solve problems in some, to develop techniques on some large scale platforms able to deal with large scale, or the streaming model or so on, also to take care of changes that happen in the network and so on. Okay, and so this is the landscape of covers kind of different ways and approaches that one is usually addressing this problem of related work. So you could have either try to do some brute force exponential algorithm because for different settings the problem is NP hard. So you could have some brute force algorithms, or you can design heuristics, for example, based on spectral algorithms or belief propagation methods. Right? You can try to enumerate all cliques or all dense subgraphs or so on. And then, as we see, you might have, depending, so we have not talked yet about measures of density. So this is just our next, the next thing that we will discuss. But it's very crucial how you define density. And depending on your definition, your problem might change quite a lot. So you might have an NP-hard problem. So for example, the clique problem is one of the hardest in computer science, very hard even to approximate. Or you might have some other definitions of density that give rise to polynomial problems. Okay, so you might have different types. So this gives kind of what is a landscape of related work. Okay, so are there any questions so far on the, yes?
Yeah, so I'm not sure I heard among those examples the problem of partitioning a graph into dense subgraphs. That's pretty much the problem that I'm working on. And the application being in entity resolution, right? Basically, you've got pairwise. Every node on your graph is let's say an incoming record, right?
Mm-hmm.
And the pairwise edges are, let's say, measures of similarity between the nodes, right? And then the task is to, partition that into entities, right? Based on those pairwise similarities.
Okay, to my knowledge, so this sounds more like this type of community detection, which also, so community detection also has a concept of density, because when you partition a graph, so you also care, you want your communities to be dense, right? So you want to be dense inside, but you also care about to be sparse outside, to have very sparse cuts, for example, right? So this is one way, I guess, to approach this problem. So for the density problem itself, so the main definitions that we will see, they don't take into account this sparse cut. So I want to find the graph to be as dense as possible. I don't really care if it is really separated from the rest of the graph. I mean, it might be very dense, and then I move a little bit and become less dense, of course, because if it was more dense, maybe I would also take this part. But that's okay. So as long as it becomes a little bit less dense on the outer, like if you see it as a core, then the cell would be less dense. Then this is your dense subgraph. And okay, then there is also the issue of finding many dense subgraphs, which I think this is, we are going to talk about that a bit. But to my understanding, this is also kind of a novel, and like there are like recent work already developed on that, and I think it's an area that is, as far as I know, is not really well understood, and there is ongoing work on that.
Sort of the problem of finding all dense subgraphs.
Well, as Bobby said before, there could be exponentially many, so you need really to have further constraints. So how do you? So the point is, if you have it's very very related to these frequent item sets. One of the problems that they face is that they have a huge output. So if, say, find me all frequent item sets, there are so many of them, so usually they produce output that is even larger than the input of their problem because of this exponential blow-up. So with a dense subgraph, you have the same situation. You might really get in a situation that I have a dense subgraph, I can change a little bit, remove one edge, add one edge or a node, and I have a graph that is almost as dense and different. So how much different do you want to be? So now one extreme is disjoint, then you allow some overlaps, but then it becomes a really interesting problem. Babis.
Could you go one step back?
Yes.
So what I would like to point out is that in the last family of objectives, where we have objectives for finding dense subgraphs which are polytime solvable, once you try to generalize into partition problems, so maximize some sort of, you fix k, the number of partitions you want, and you want to maximize the sum of these objectives, then they also become NP-hard as well. So as soon as you transition from finding one dense to k partitioning problems, they tend to become NP-hard problems. As a comment.
I don't want to get too deep into my problem, but I don't have a K. I'm basically trying to find, I want it should be dense within and sparse between my partitions, but there's no K.
So correlation clustering is one of the methods that doesn't have k as a parameter naturally. So I can tell you more about this.
Okay.
Yeah.
But that's not.
No. So
Part
we
of this
focus on.
Yeah, slightly different problem.
Right.
Yeah.
Yeah.
Okay, so let's try to be more formal, define our problem more formally. Okay, some standard notation. So I have a graph, vertices, edges. I work with a degree of a graph. I consider edges between two sets. If I have a set S and I have a set T, I consider the edge in between. And I use this notation e to the, there is no like pointer, right? Okay. I use e to the s to say the edges within a set of vertices S. Then I define a graph cut, which is defined as a set of vertices. And then I also usually consider the complement. And the size of the cut are the number of edges that go from the set S to its complement. And so then I also consider induced subgraphs. And I also consider triangles. So when I have a set S, I can take the set of triangles that are all triples for which all three edges are present, and so on. So, but okay, this is our notation. And now we say, okay, I have talked like almost for 1 hour. So talking about density, what are the measures of density? So what do we try to do? What type of function we want to optimize? We already mentioned the most standard notion of density in computer science is clique. And this is complete density, like so like full density. So this would be this this graph here, and the red nodes form of a clique. Everyone is connected to everyone. So this is perhaps the most standard in computer science, but it's also the most strict definition, right? So in real networks, probably this will not happen. I always have noise and some of the edges missing, and so on. So it's very unlikely to have complete cliques, especially large cliques. So then I will focus on other types of density that allow me to deal with this noise. So one notion of density that I will deal is the edge density. So in that case, I say that the edge density of a subset the number is proportional to the number of edges in the density divided by the number of vertices. And this is also equal to the average degree, if you have these two here. Sometimes I just drop 2 because it's a constant factor and I don't care. Sometimes I leave it. Okay. So this is another concept of density. Then another definition of density is the edge ratio. So in that case, I take again the number of edges on my subgraph. Instead of divided with a number of nodes, I divide by the number of all possible nodes, all possible edges in my subgraph. So notice that here is the average degree, and this could take values larger than 1. Here, the edge ratio is always between 0 and 1, because I divide by the denominator is always larger. Then when I look at triangle density, I will take the number of triangles divided by the number of vertices on my graph, or I can look at the triangle ratio, which is defined similar to the edge ratio. Okay. There are other concepts of density. For example, there is k-core, right? So k-core is a maximal subset of vertices that every vertex in the subgraph has at least k other, is connected to at least k other vertices on the subgraph, right? So this is the k-core, and it's also very popular in social network analysis and so on. Yet another definition is alpha quasi-clique. So here, the motivation here is the following. So if I had, consider the edge ratio, for example, that I had before. So assume that I want this to be the edge ratio larger than alpha, some fraction alpha. Then given a set S, I would say that this is an alpha quasi-clique if the number of edges are at least, if its edge ratio is at least alpha. And this is formulated as that the number of edges is greater or equal alpha times all the possible edges. Okay, so this is, again, is a definition that allows for some noise. So I don't look for a complete clique. Okay, there are many other notions of density. So it's it's easy to define notions of density, but we are not considered in this tutorial. So we'll focus mostly on the edge density, on the k-core, and the alpha quasi-clique, and perhaps some other. But just for completeness and for your notes, there are also other definitions that people have studied. And before proceeding, let me just make a reminder of 2 problems that we will use in the rest of the tutorial. So they're very, in some sense, similar problems, but also different. So one is the min cut, the other is the max cut. So in the min cut problem, I have 2 designated nodes, S and T, and I want to find a small cut between S and T, right? So for example, this could be a cut that separates S and T. So what is interesting, this problem is polynomial time solvable, and the problem is equivalent to max flow. Okay? Another problem, seemingly similar, is the max cut problem. In this problem, I don't have S and T, so this one difference, and I don't look for a small cut, I look for a large cut. So here, for example, this is a good max cut because I really cut a lot of edges, right? So from S to its complement. So now, although these problems look similar, they are different in their complexity. So the min cut is polynomial, max cut is NP-hard problem. And but there are nice approximation algorithms. So you can have a half approximation because the function is submodular, or you can have a very advanced method, very elaborate method based on semi-definite programming and offers a good approximation guarantee. Okay, this is just for you to remind, right? So I don't know if you are familiar with these problems, min cut and max cut. Okay, and then, so this was for our preliminaries. Are there any questions? So now we will really start working on problems on density, how to find dense subgraphs. So somehow now we start like giving all of this background and all of the tools that we needed. So are there any questions up to here? Okay, so let's start. Okay, so now we are going to talk about our first problem, which is how to find a dense subgraph, and we will consider a particular notion of density, which is the degree density. Okay? So do you remember what is the degree density? So can somebody just tell me to see if... Is the average degree. So I have a subgraph, and I look the number of edges in the subgraph divided by the number of nodes. Okay, so this is the average degree. And now my problem is I'm given a graph, and I want to find a subgraph that maximizes this density. So what do you think of this problem, actually? Do you think it's NP hard, it's polynomial? Let's make a poll. Who thinks that this problem is difficult in the sense NP hard, and who thinks it's polynomial? So NP hard, who thinks? Don't count me, I just try to confuse you. So NP hard. So Mirella, 2, 3. Polynomial. 1, 2. Okay, 3, 2. You got? You raise your hand for polynomial? Yeah. Okay, so 3 to 3. So there is no winner. Okay, so a lot of excitement. So let's see what will happen. Okay, so it turns out the problem is polynomial. Okay, it's quite counterintuitive, because when you think about these dense problems, you really think of the clique problem, which is really a hard problem. But then it turns out that once you define your problem like that, just the average degree density, then the problem becomes polynomial. Okay, so let's see why. So this is the paper I mentioned, this key paper that goes back 30 years, and it's due to Andrew Goldberg. Okay, so what Goldberg did, in my opinion, was quite ingenious. So he transformed the problem to a mean cut instance, right? So he took a graph and said, okay, I want to solve, to find the densest subgraph. I will take this graph, I will transform it to another graph, and in this graph I will solve the mean cut problem. Mean cut problem is polynomial, and my solution would transform to another solution for the original problem for the dense subgraph. Therefore, I solved my original problem of density in polynomial time. So he said, okay, I look at this graph, and is there a subgraph S for which the degree density is greater than some number C? Okay, and transform this graph to this graph. So he added a no, I will see the transformation, and in that new transform graph, he asked, is there a small cut with a certain value? Okay. So let's see why this works. So, okay, there's a little bit of kind of derivation, but let's not really go through. But it's very simple. You can, if you are interested, you can really verify it on your notebook. So the question I want to ask is the following: is there on my graph, is there a subgraph with density at least C? Okay, so the definition of density is this one. So I take this definition, and then I rewrite this expression here. Okay, multiply by C, and then look at the edges, how they look, and write them with respect to the degree, and adding and subtracting. Okay, standard algebraic formulations, and then this question is my, do I have a subgraph with degree density greater than C, translates to this question, which says, is this quantity satisfied? Can I find some set S that this quantity is satisfied? So this is, let's not parse it yet, but this again some quantity that depends on S, its complement, the degree, the edges that go between S and its complement, and so on, right? So these questions are equivalent. So if I can solve the second, the one at the bottom, I can also solve the one at the top. Okay, now, so this is the equivalent expression. Okay, now what Goldberg did and what is the transformation is the following. So this is my original graph. So I just put it just on a row. So these are the vertices, and if there is a vertex, an edge on the original graph, I put it here. And then I put also a special node S, a special node T, and for all nodes on the graph to the source, I put a capacity equal to the degree of the node. So, for example, this has degree 1, right, on the original graph. So this would be capacity 1, while this has degree 1, 2 on the original graph without counting the source and the sink. So I will put here a 2 on this, on the second edge here, and so on. So here I put the degree as capacity. Here the capacity is C. So C is a parameter, the value that I want to see if there is a subgraph that has density at least C. Okay? So this is my transformation. And now I want to ask this question. Is there a set S that this kind of inequality is satisfied? Okay. You notice, the first thing that you notice is that this graph here has a cut that has a value exactly 2 times C, right? Remember that the sum of degrees on a graph sums up to 2 number of edges, okay? So this value here is always a cut, right? So the question is, can I find a smaller cut? Okay, that is not this kind of trivial cut, right? Let's assume that this is another cut, okay? So that I just go through some of the, so this is the only kind of, the only way to make a cut that is not as trivial as the first one that I showed you before. Okay, let's see that I'm able to find such a cut, right? What would be the value of this cut? Okay, so let's see. So for the values on S prime here, so this is the S bar, the complement of S, the value of the cut would be the capacities that go to the source. So this would be this term here. Right? So the values, the edges I cut in the graph, they're here because they go from S to S prime. And the values, the edges that I cut from that part, they are this term, because I have S, the number is S, and each one of them has capacity C. There's this one, right? So if I'm able to find such a cut, it means that this question has answer yes. There is a cut that its value, which is this term, is larger than this, which is this kind of trivial cut that I showed you before. So since I solve this, since I can solve this question with a mean cut, and since this question is equivalent to finding this max cut, sorry, this dense subgraph, then it means that the dense subgraph problem is polynomial. Okay? Yes?
This transformation allows to find the solution in polynomial time.
Correct.
By the way, does it guarantee to find out older solutions in polynomial time?
What do you mean all the solutions?
So here, it can find one.
Yes, but
solution is tons.
so okay, so this is a polynomial time. Mhm.
Our original problem is to find out the order.
No, my original one was to find one. I want to find one dense subgraph. Yes, we are in this setting. We have not yet gone to the setting that I'm looking for many or for no. So okay, so actually we excluded. We said we are not going to find all because there could be exponentially many. So we will consider some problem formulations that you find k, kind of I give you, find me 10, and then you can do that. But before going there, the first step is to be able to see if we can find one. Yes, please.
So one thing is, in algorithmic graph theory, in the chapter of connectivity, let's say, there exist algorithms that can enumerate all mean cuts, so you can do it. But as we said, they can be an expression of Nagramoki, Baraki.
Right, then I guess so you can use the same construction and then you find all from all mean cuts and then find all dense subgraphs. Okay. Okay, there you go. Okay. But did you see the mapping and so in my opinion this is quite ingenious. I don't know if you like this transformation. Did you guys, you have any questions? Okay. So can you see the cuts actually? Everything is clear for you? Perfect. You think this you can, what is the cuts here? Okay, so my original question was, is there a dense subgraph with density more than C? And then if C is given, I can solve this problem. But my original problem was finding the densest subgraph without knowing C, right? So if I don't know C, then I cannot really make this construction. I cannot put this. I mean, I can make it, but I don't know exactly what to put on the capacity on the edges on the right? But okay, maybe perhaps there is no problem. I can try many different values of C. So this is my algorithm, Goldberg's algorithm. I said goes from 84. So I'm given the graph, I give this parameter C, and I ask if there is a graph, a subgraph that has density at least C. Then I do the transformation the way I explained. I solve the min cut, and then if returns the empty set, so just this non-trivial construction, then I return my S, and this is my dense subgraph. Okay, I don't know C. Actually, I can do a binary search and see for which value of C I can get. So what's the largest value of C that I can get a non-trivial solution? So you can do it binary search. You can do logarithmic number of min cuts. It turns out you can, actually there is, because this kind of min cut problem instance has a special structure that admits solutions of parametric max. I can apply the parametric max flow algorithm. I can just do it with one value of min cut. Okay?
C is not an integer, is it?
No. Well, no, it's not an integer. Yes. Well, but you can do. I mean, you can do binary search still. You have a value of accuracy. Okay, so yeah, so you have polynomial number of possible values that can take. So you can bound the So you can because it's edges divided by nodes. Yeah. Okay. Okay. So then I'm kind of happy because I saw how I can find the densest subgraph problem exactly, mapping to a problem I know, min cut. There are many efficient algorithms. Okay, what is the problem here? One issue is that for doing this min cut, I still have to do, so the state of the art is an algorithm that is n times m. So, okay, even if the graph is sparse, m is at least n, so this is at least quadratic, right? So I cannot really do it for graphs of millions or billions of edges, right? So I need to do something else. Okay. And then what's something else? So there is another very nice work now that we will talk. So this is the faster algorithm of due to Moses Tsourakakis. This is a greedy algorithm. So it's very simple to implement. And this algorithm is an approximation algorithm. So this is kind of a little bit kind of unusual in the sense that we typically have approximation algorithms for NP-hard problems. In this case, Moses Tsourakakis devised an approximation algorithm for a problem that's already polynomial. Okay, so one might say why this is so. Okay, this is because to find the exact solution is quite expensive, and we cannot really do it for large graphs. But this is a linear time algorithm, and you can solve your problem in linear time. Okay. So this is the algorithm. So I'll first give you an illustration of the algorithm, and then we will see how it works. So let's say that I'm given this graph, and I want to find a dense subgraph. Actually, how would you do it? What would be your intuition to find a dense subgraph? Let's say you don't, now you know this kind of fancy transformation to the min cut, but let's say you don't know, so intuitively, what would you do? Look for high degree, so you find, let's say, the high degree, and then? Okay, grow up. Yeah, actually, very good. So this was also my intuition, that you kind of do greedy, and you start slow from the you grow up. So this type of So this is also what I thought. Okay. It turns out this algorithm is it doesn't. You can fail with this algorithm. You can really make it perform bad. And what to do is exactly the opposite. So that's why I find this very nice, very surprising. So you start by the very low degree vertices, and you remove them. So you first find this guy, you remove it, right? So then this is, you find the other one, you remove it. And then now you have a choice. So you have two vertices with degree 2, this one and this one. So you pick one of them, this one, let's say, and you remove it. And you keep doing that. So now you have again a vertex of degree 1, you remove it. And you keep doing that all the way until you reach to the empty graph. So you have removed everything. Okay? Okay, yes?
Exactly the way you find the k-shell, right?
Is the way you find, yeah, K-core. So it's the same, it's a K-core algorithm, yeah. Okay, but the difference comes here. So in K-core, you have this layer of the different K-cores for different K and so on. So here you do it all the way. You do the empty graph. And then you look at all of them, all these algorithms, all these graphs that you have generated, and you say, okay, which was the densest one? So I generate n different graphs. Which was the dense one? Okay, here I just happen to find a click, but this also is the one that maximized the average degree. So you take it. So this is the algorithm. Okay? So very simple, very nice. Okay, this is pseudocode. I don't go through that. Let's make a very quick proof of why this works. Okay, so what we are going to prove is that this algorithm gives you a factor 2 approximation guarantee. Okay, let's see why this works. So this is the argument by Couler and Saha. So let's say that S star is the vertices of the optimal solution, and let's say that my density, the maximum degree density is equal to lambda. So this is the density of the S star. Okay. Now, I claim that all vertices on S star, their degree inside, so they have at least lambda neighbors inside S prime, inside this optimal solution. Okay? So why this is so? This is because I assume that this S star is optimal, because this means that, let's assume that, so since S star is optimal, I know that if I remove any node, the density is going to decrease, or not to increase, let's say. Right? So if I remove any V, so this would be the density of the new graph of S star minus V, because I remove so many edges, and I remove one vertex. So I know that. So then this means, so if I just rewrite this, I know that the degree of V inside the star is at least lambda. Okay? And once I know that, then the argument continues as follows. Then you say, now consider the greedy that I just showed you, right? So you remove the minimum degree vertex until you're left with empty graph. So now, so look at the set that the algorithm has just before removing the first vertex from the optimal solution. So the total number of edges is at least this much, right? Why? Because the degree, I just saw before that the degree of each node in V, and V is V star because this is the first vertex that I removed from the optimal solution, it has degree at least lambda. This is what we saw before. Okay? So this means I have so many edges. So this means that my density on this S, which is the set of vertices just before removing the first vertex from a star, is at least lambda over 2. So I assume that the optimal is lambda. Therefore, I get my factor 2 approximation. Right? So very neat. Okay, so what do we know? So we know that this is a factor 2 approximation. It runs in linear time. So the linear time actually is not obvious, but you can see it, and it's linear time for unweighted graphs. If the graph's weighted, then I have to use heaps, and a logarithmic factor enters here. And things are not as straightforward for directed graphs. So I think Babis, I think I'll skip for the directed graph so that you have. So what happens for directed graphs? I have very similar story. So okay, I'll just give you the definition. So density for directed graphs, one way to define it is this way. So this will be an extension of the degree density that we define for the unweighted case. So in that case, I want to find two sets of vertices, S and T, and I look for edges that go from S to T, and then this is, instead of just dividing, I divide by the geometric mean of the two sets S and T, so, right? So now, and this problem has very similar kind of properties with the problem we talked before. So it's although the first paper provided a logarithmic approximation factor, it turns out that you can solve this problem in a polynomial time using a linear programming. So Tsourakakis first came with this linear programming. It was quite expensive linear program because you have to run. Yeah, so okay. So this is an exact linear program. He also gave a greedy, but this was not like the greedy before, one-time greedy. But he had a parameter, and he had to run this greedy for many different values of the parameter, for n squared times of the parameter. So the algorithm had cubic complexity, right? And then this was later improved to, so first of all, the LP was improved, and Kuller and Saha provided the exact algorithm, which is based on max flow instead of LP, so it's much easier to implement. And also they improved the running time of the greedy, so they did not have n square calls to the greedy, but they managed to do it with one call to the greedy. And the greedy is very similar to the one I said before. So you have your set, you remove edges with a minimum degree until you left with empty graph, and then you select dense subgraph out of all the subgraphs you have generated. So, okay. So for the slides are here. For lack of time, we don't go in the details. So before giving the floor to Babis, so what do we learn? So we learn that for the degree density measure, we can have exact algorithm, can work both for undirected and directed graph. So these algorithms are based on flows, so they are not so easy to implement. But instead we have linear time two-factor approximation algorithms achieved by greedy. So how good are these subgraphs? Actually, we don't know at this point, because this was the first measure that we studied, right? So, okay, it gave us, so the question is this really this degree density a good definition? Okay, we would like to find this out. How we are going to find this out? It will be by studying other measures. For example, the quasi-clique or the k-core or the edge ratio that I talked before, and try to compare from an application point of view or using different techniques, right? So this is of interest. Another interesting thing, okay, you already asked that this is for returning one dense subgraph, not all, but also notice that I don't have any control over the size. If I tell you, find me a subgraph of size 100, I don't know how to do that, because this method just gives me one with no constraint on the size. So this is also something that Babis will talk about. So we switch here.
So the break is in 15 minutes?
Yeah, let's see. Okay. Yeah.
So hello everyone. So I will start my part by discussing the Edge surplus framework, which we introduced a couple of years ago at KDD. So this is more of an abstraction that generalizes many existing density measures. In particular, we asked the following question. So what are the kind of properties that the density function should satisfy? So what we're going to define is a function f, which, as you can see here, is the sum of two functions, g and h. So the first function g takes as argument the number of edges induced by the set S, and the function h takes as its argument the cardinality of the set. So intuitively, what we would like in many applications is a function g that rewards the more edges that we have, okay? So at the other hand, we want to penalize big sets, right? We don't want to keep adding vertices just in order to increase the number of edges induced by S. So we found out that many of the existing measures of density
fall under this framework. So G is an increasing function of the induced edges of S, and H is also increasing. So we reward edges, we penalize size. The optimal G, H surplus problem is the problem of finding a subset S star for which this function is maximized. So let me give you a couple of instantiations of this H surplus framework. So if we set G and H to be the logarithm function, then you can easily see that where the optimization problem is asking to maximize the log of the average degree, of the degree density. So I will call average degree even if the 2 is not there, okay? Because the same thing. So the second thing, if you forget for a moment the monotonicity property of H, is that if you set G to be the identity function and H to be 0 if X equals K, so if we restrict if we ask the problem of finding the densest subset of vertices with exactly K vertices, then we can solve this by setting H to be a function for which takes value 0 if X equals K, otherwise plus infinity. So this is known as a K-densest subgraph problem, and we're going to mention it later. It's a very hard problem, and many interesting open theoretical questions are open with respect to this problem. In particular, closing the gap between upper bounds and lower bounds.
By the way, in the case HEX is not increasing function.
Yeah, that's what I said. That's an exception. So this is one of the few exceptions of this. So if you forget for a moment the monotonicity of H, but my point is that this framework, if you relax and take other kind of properties, you can actually find out many of the existing densities. Most of them, however, fall under this increasing function property. So a special case for which G is the identity and H is some parameter alpha between 0 and 1 times X choose 2. Then we get an interesting problem which we call the optimal quasi-clique problem. This is from a KDD paper 2 years ago, which turned out to have some nice properties. And one last observation that I would like to make, so I showed you that if you set G and H to be the logarithm functions, you get the densest subgraph problem. You can actually set G to be the identity function and H to be alpha times X. So you get the problem of maximizing the number of edges induced by S minus alpha times S. So even if this problem is not the densest subgraph problem, it actually, as we showed, by trying out the polynomial number of values for alpha and optimizing this, we can actually solve the densest subgraph problem by finding the maximum value of alpha for which this value is non-negative. So the densest subgraph problem can be formalized in 2 ways using this framework. And you can solve it using log n binary search queries instead of trying out the polynomial number of choices for alpha. So in this framework, if you set G to be the identity function and H to be a concave function, then you get a family of objectives which are polytime solvable. And the idea is pretty simple. By standard properties of supermodular functions, the edge surplus optimization problem under these conditions ends up being a supermodular function, and we know that we can maximize these functions in polynomial time. So it turns out that most of the interesting objectives, instead of being concave, they turn to be linear functions of H. And this can also be justified from a theoretical perspective. The optimal quasi-clique problem was shown to be NP-hard, and I used it also for partitioning a graph, for the balanced graph partitioning problem. In this tutorial, we're not going to discuss this framework of partitioning a graph, but just let me mention that the idea of actually taking a graph and splitting it into K parts, which roughly have the same number of vertices, and minimize the number of edges across the cut, is a very important problem in distributed computing. So I used this edge surplus framework to come up with relaxation, a Lagrangian relaxation essentially, of the balanced graph partitioning problem, which turned out to give state-of-art performance. And you can find out more by Googling Fennel. So for the optimal quasi-click problem, there was an adaptation of the Charalampos algorithm. So the idea is you remove the smallest degree vertex, and then you can show some approximation guarantees for this problem. I won't discuss that, but I would like to discuss in further depth the fact that we've seen, so Aris showed the landscape of related work. A very interesting problem is, he also showed a couple of applications where we need to find subsets of vertices which are large near cliques. So the problem of finding large near cliques in real world datasets is a notoriously hard problem. There exist many tools out there that suffer one way or another. So the densest subgraph problem, for instance, I'll give you also some numerical evidence, turns out many times to fail with respect to finding these large near-click subsets. So a very interesting question is asking whether there exist polytime solvable objectives that we can actually understand very well and we can solve efficiently that actually succeed on this notoriously hard problem on real data. In particular, here's the question: can we combine the best of both worlds, namely have polytime solvable formulations, and also these formulations should be successful with respect to finding large near cliques? Because you can imagine if I give you a large who calls whom network, for instance, it's a graph where every vertex is a human or a phone account, and we have an edge. If we exchange a phone call, finding these subsets of large subsets of vertices with many edges is essential for many security applications. So being able to solve this problem in practice is a very important problem. And recently I had a paper in DubDubDub where I introduced a generalization of the densest subgraph problem, which actually has some very interesting both theoretical and also application properties that I'm going to show you. So let me start with the definitions. So for any subset of vertices S, we define the k-click density, rho k of S, to be the average number of induced k-clicks, okay? So Ck of S is the number of k-clicks induced by S. That means all k-clicks whose all vertices are within S, okay? So the k-click DSP asks to maximize this density. When k equals 2, Aris already showed that this is a densest subgraph problem because a 2-click is just an edge. So rho 2 of S is the degree density. So as soon as we move to other values, it was not known whether these problems could be solved in polynomial time. For the special case of the 3-click DSP, so maximizing the average triangle density, I will call this problem the triangle densest subgraph problem, and this is the notation I'm going to use. So the first question is, how different can the DSP be from the triangle DSP? And the answer is, in theory, it can be radically different. For instance, you can come up with many examples, but the most trivial one is if I have, let's say, a complete bipartite graph or a triangle, and the triangle, let's say this is my graph, the union of these two things, the one objective will return the bipartite click, the DSP, the other one will return the triangle, as bipartite graphs have no odd length cycles. So the interesting question is what happens on real data, how different is the behavior of these two objectives, and whether we can actually solve the k-click DSP in polynomial time. Well, you can think that if you can solve the k-click DSP for any k in polynomial time, this is very unlikely, because I can solve the max click problem, but what we're going to show is that for any constant k, we can do it in polynomial time. So first, there exists an algorithm. The first theorem from the DubDubDub paper is that there exists an algorithm which solves the triangle DSP in runtime, in polynomial time, and in particular, it runs in m to the 3 halves. M is the number of edges, plus n times t. T is the number of triangles in the graph, plus the minimum of these two quantities raised to the cube. So I will sketch you an idea which has an extra logarithmic factor which can be removed by using parametric maximum flows. And furthermore, more generally, we can solve this problem in polynomial time for any k constant. So let me sketch out the idea of the polytime algorithm, and then we'll have the break. So the idea is pretty similar to Goldberg's algorithm. The main difficulty that arises is that when you have a set S of vertices, when you solve the DSP, you can have an edge either induced by S or going out from S. Okay? When you have triangles, you can have triangles with different number of vertices within the set S. You can have induced triangles with all three vertices inside, but you can also have two or just one vertex of a triangle. And this complicates things in the sense that if you take Goldberg's network construction and you try to put different capacities in order to make his algorithm work out, to my knowledge, this is not possible. And I conjecture it's not possible. So the idea is we're going to ask whether there exists a set S with induced number of triangles greater than alpha times S. So alpha is going to be a parameter, and where the idea is similar, we're going to try out logarithmic number of values, because so the first thing to notice is that the triangle density is always, the optimal triangle density tau star is lower bounded by 0, of course, and upper bounded by the density for the n click, okay? Also, a more non-trivial lower bound, still very easy to see, is that the triangle density tau star is lower bounded by the number of triangles divided by n, because simply the whole graph is also a feasible solution. That's one observation, and the second observation is that if you take this range and you discretize it by spaces of 1 over n squared, then you know that you are good enough, because any two distinct triangle density values are far away by at least 1 over n squared. So it turns out that you have at most 4 log n queries to make for alpha in order to solve this problem. So as I told you, Goldberg's construction that Aris showed in the beginning won't work out. So the network construction is, this is one. I have 2 more in a KDD paper that will appear this year in a few days. I will present here. So let me show you one construction. So we create a bipartite network. On the left-hand side, we have one vertex for every vertex in my graph. And on the right-hand side, I have one vertex for every triangle in my graph. And then I have a source and a sink. And sorry, I will abuse a little bit the notation for the sink just to use standards. T will be also the notation for the sink. So from S to V, I'm going to have actually an arc of capacity equal to the number of triangles that V participates in. So this is shown for the K-click DSP. From V to the sink T, we're going to have an arc of capacity K times D. Actually, this is alpha. This is supposed to be alpha. This was a different figure, but it's the same thing. From V to every triangle, or K-click, I'm going to have an arc of capacity 1. And in particular, there are going to be FKV outgoing arcs, and they are going to direct towards the K-clicks that V participates in. So V as a vertex has a given number of triangles or K-clicks, and I'm going to add arcs from V to this set of K-clicks. And then from this set of K-clicks or triangles, I'm going to have arcs, K outgoing arcs. So if it's a triangle, there are going to be 3 outgoing arcs of this capacity, a very large number, okay, that you can actually, I call it plus infinity, but you can actually, it's a very big constant that depends on n that you can actually compute. So this is the network construction. This is just one. There exists more network construction. So in particular, let me see. Here's the K-click DSP. As I said, CV is the number of K-clicks that V participates in. You can have also arcs of capacity K minus 1 here. So if it's this is a triangle, what you do, you take your graph, you list the number of triangles, you create this bipartite network, one vertex for every vertex, one vertex for every triangle. K times alpha arcs from the vertex to the sink. K minus 1, the capacity from every K-click to the K vertices that it's consisted of. And from every V, we have CV outgoing arcs to the K-clicks of V. This is the construction. And the algorithm, it's a binary search. So you start with the obvious lower bound on the triangle density and the obvious upper bound on the triangle density. And then, as I said, while this condition holds at only y, because these values are separated by 1 over n squared, then you construct a network, you compute your max flow, you look the minimum st-cat, and if this st-cat, so if you look the s side, and you have more vertices than just s, then you know that you can set this thing to be alpha, okay? So you know that you have found one set with density at least alpha. Otherwise, you set your upper bound to this value, okay? This is the idea of the algorithm, and the runtime, n to the 3/2, the time to list triangles. There exists better algorithms, but I want to keep the complexity as simple as possible. Output-sensitive algorithms by Rasmus Pei, Virginia, Vasiletska, and collaborators. And this is an algorithm that can be used to solve max flows on bipartite networks that are very imbalanced. So it turns out that the number of triangles in many graphs, actually most graphs, is way larger than the number of vertices. So by invoking an algorithm due to Orlin, Cliffstein, and collaborators, this turns out to be a very good choice for this particular problem because this bipartite network is highly unbalanced. So the space complexity is n plus the number of triangles, and as I said, typically t is way greater than the number of vertices. So I think this is a good point to have the break, and we'll continue in 25 minutes.